Hello and welcome everyone. I've got Eric Wagner on here as well. We'll go ahead and get started in interest of everybody's time. Welcome to After the Blast, the Ecological Recovery of Mount St. Helens. Throughout the presentation, please feel free to enter any questions that you may have for Eric from your Zoom Q&A feature. After his talk, Eric will be answering your questions live and posting responses. And the full video of the webinar will be posted later. You should be able to access the Q&A button from your Zoom panel. And so to get started, it is such a pleasure to have you all here in this webinar during this truly remarkable time. While I'm sure that the year 2020 will certainly stand out due to COVID-19, we're here today to reflect on another historic event that happened just about 40 years ago today, 40 years ago on May 18th, the seismic activity and the catastrophic eruption of Mount St. Helens. I know that there are likely many folks here today who may have been in the Pacific Northwest at the time of the eruption and probably have very vivid memories of where they were and what they were doing on May 18th, 1980. It's really a privilege to reflect on where the mountain and its ecological inhabitants are 40 years later and marvel at their resilience. Our featured speaker, Eric Wagner, is a science and nature writer whose work explores the pressing scientific and environmental issues of our time. Eric has published 3 fantastic nonfiction books, and his journalistic writing has appeared in The Atlantic, The Smithsonian, High Country News, Orion, and Slate, just to name a few. Eric spends a lot of time thinking about how we humans are or are not willing to share the planet with our fellow non-human residents. Like many here today, Eric is a UW alum. He earned his master's degree in English at the University of Washington. He earned his PhD in biology at the University of Washington for his work with penguins in Punta Tombo in Argentina. There he was observing the world's largest colony of penguins alongside his supervising UW biologist, D. Boersma. A decade later, Eric would chronicle his time with Professor Boersma in his book, Penguins in the Desert. Another vital link between Eric and the UW is his relationship with the University of Washington Press, the university's publisher, and the oldest and largest producer of scholarly and general interest books in the Pacific Northwest. UW Press works with authors like Eric to produce books that shape public thinking, conversation, and action in the Pacific Northwest, in the United States, and across the world. In 2016, the UW Press published Eric's first book, Once and Future River, Reclaiming the Duwamish, co-authored with Seattle Times photographer Tom Rees. In this gorgeous volume, the Pacific Northwest Quarterly praised it as a multifaceted narrative of evolving relationships between people and the river. Eric and Tom's images and stories highlight the complicated relationship between Seattleites and their only river, a waterway that has been strained, polluted, and neglected by those who have benefited from it the most. Eric and Tom movingly revealed the story of the Duwamish River's changed beauty and possibility for the future. Today, we are so pleased to have Eric with us to share his latest book with the UW Press, After the Blast, which is the story of a volcanic region's astonishing recovery in the days and years following a historic seismic event. Publishers Weekly has hailed the book as a superb look at scientists and science at work. The writer Robert Michael Pyle said, After the Blast is a story of the greatest ecological experiments in Northwest history, told with beauty and verve by one of our best biology writers. In a fascinating journey through the blast area and beyond, Eric reveals a surprising picture of how life responds in the face of seemingly total devastation. Eric lives here in Seattle with his family and 2 very demanding cats. I'm very, very pleased to welcome Eric Wagner.
Hello, thank you for joining me. And I was going to say thank you for coming, but the times being what they are, I'm grateful to the University of Washington Libraries and the University of Washington Press for making it possible for us to spend some time together today. I'm going to talk to you a little bit about my book, After the Blast, The Ecological Recovery of Mount St. Helens, which is out now just in time for the 40th anniversary of the 1980 eruption. And so this is what Mount St. Helens looks like today, as seen from the Mount Margaret backcountry a few miles away to the north. And it's a real for Pacific Northwesterners, it's a really sort of iconic scene, and also a real regional marker. While I was doing research for the book, I would talk to a lot of folks, and everybody who was alive in 1980 in this area remembers the moment, of the eruption, and they know where they were, and they know what happened. They remember what it was like to hear about it. And in a way, this makes the story of the eruption a very known story. It's very familiar. And so one of the things that would happen when I would tell people that I was working on a book about the 1980 eruption is they'd be like, or about Mount St. Helens, is they'd say, "Oh, what are you going to say that's new?" And this was at a time when I was trying to read, dozens of books and papers and research reports about all the research that had been done at the mountain over the past 40 years. And to me, it was all new. It was just a surfeit of information, and I was having trouble wrapping my mind all around it. And so part of the thing that I want to do today is show you what is new about the mountain and talk a little bit about some of the research that has happened there and some of the lessons that we've learned in the intervening 4 decades, because there are a bunch. But first, I want to situate the mountain for you a little bit. So Mount St. Helens sits in the Pacific Ring of Fire, the so-called 25,000-mile arc that goes from the southern tip of South America up through Central America, through North America, across the Aleutians, down Russia, Japan, into the Indonesia, the Philippines, and down to New Zealand. And all of this ring of fire is marked with hundreds of volcanoes, over 400 of which are still active. And Mount St. Helens sits in the Cascade Range, which runs officially from southern Canada, which you can't see here because this is a US government image, so to them, Canada doesn't exist. But there are a couple of volcanoes up in Canada, and it runs down to Northern California, as you can see at Lassen Peak. 18 volcanoes make up the Cascade Range, and Mount St. Helens is the youngest of them by a fair bit. The vent over which the mountain sits is only about 40,000 years old. And the prominence itself, what we think of as the mountain, is younger still. It's only 4,000 years old. And so in geological terms, Mount St. Helens is really just a baby. And it's as babies go, it's pretty squawky and demanding of attention. It's by far the most active of the Cascade volcanoes, and it erupts about every 140 years on average, people have found. Not that you would have known this in 1979. This is an image of Mount St. Helens from them, just showing what it looked like before it blew. And Mount St. Helens, sort of owing to its youth, was considered the most beautiful of the Cascade volcanoes, and its peak was the most symmetric. And in part, this was because it wasn't as old as Mount Rainier or Mount Adams or some of the other peaks that had their summits scoured by glaciers. And so they had a more sort of rumpled appearance. But Mount St. Helens it was called the Fuji of North America. It was really quite lovely. But in the spring of 1980, in March, in the middle of March, human and geological time horizons sort of met when a series of small earthquakes shook the mountain, which was a signal to seismologists and sort of volcanologists that magma was on the move underneath the skin of the earth. It was moving up. And so it was moving up into the prominence. And so beginning in March and continuing into April, magma began to fill a chamber under the northern flank of the mountain, and the chamber began to expand or bulge. It became known as kind of the bulge. And so this is an image from April of 1980 showing the bulge, which by that point was expanding up to about 5 feet per day. You can imagine the rock just sort of pushing out as magma fills it up. And so as this was happening, there were a number of steam eruptions, and sort of ash and steam began to pour out. This is also from April of 1980, and you can see how Mount St. Helens, which was all snow-covered, was becoming quite dirty with ash. A crater opened up on the summit, and these giant cracks appeared. And then for a little while, in the beginning of May, seismic activity sort of subsided until May 18th, 1980. And so this is what I'm going to show here is a series of images taken by Gary Rosenquist, who is a photographer who was camping in Bear Meadow, which was about 11 miles east of the mountain. And this is a photo that he took at 8:27 a.m. And at 8:32, 5 minutes after he took this photo, an earthquake of 5.1 on the Richter scale shook the mountain. And that precipitated what is known as the debris avalanche. So all this, the northern flank, which was really unstable, just collapsed in a tremendous landslide. It was the largest landslide recorded in human history at the time. And so all, billions and billions of tons of rock and glacial ice and rubble just cascades down in this huge wave of debris. And when that happened, the northern flank had sort of contained the magma chamber. There's all this superheated water and gas in the chamber that's being sort of kept under wraps by the mountain. But when the landslide happened, all of the pressure that was holding the water in place was released. And so it all exploded out in what is called the lateral blast. And so Rosenquist captured those moments of the landslide debris and the lateral blast, the start of the lateral blast here. And they're really, you can see it's really quite something. And so the next image, this is a GIF of more of the lateral blast as shown by a photographer I'm not sure who took this, but he was standing on the western side of the mountain. And so you can see just how quickly once the mountain went, it went profoundly, I guess you could say, just out it goes. And so once the landslide was done, once the summit and the northern flank had rolled away and the lateral blast left behind a crater, ash began to billow from that crater, a giant ash plume, which is also known as a Plinian column after Pliny the Younger, who watched the eruption of Vesuvius. And so the ash rose, I think it was 15 miles in under 15 minutes. It rose 15 miles into the sky. It was about 500 million tons of ash. And then it began to sort of blow east in the prevailing winds. And you can kind of see this here, this giant plume just sort of spreading out. And so it reached Spokane in the middle of the day and dumped many inches of ash on the ground. And then it just sort of rose and continued on. Traces of ash were found in 17 states and before the plume rose into the stratosphere, and it circled the Earth in about 2 weeks. And then after the ash plume began, so the ash is billowing out all afternoon, and then, beginning in the morning and going on in the afternoon. And then in the afternoon, what are called pyroclastic flows began as scorching hot volcanic rock called pumice begins to kind of froth out almost over the new crater rim and spill down the slopes and covered this large sort of mat in front of the mountain. And so the main eruption, the sort of what's called the cataclysmic eruption, lasted about 9 hours. So after 9 hours, the ash plume dissipated and the pumice, the pyroclastic flows stopped. And this was kind of what was left. And Mount St. Helens had gone from having that perfect symmetrical peak. It shed 1,300 feet of elevation. It had this gaping crater that was more than a mile in diameter and 2,000 feet deep. And so it was, it's pretty awesome and apocalyptic to see, a mountain that has been just sort of radically hollowed out over the course of about a day. But this is what it looked like from a landscape perspective. So this is sort of a composite image taken from a number of NASA sort of satellite images. And what you see is how sort of much the mountain's eruptive effects spilled out. And this had sort of taken people as a surprise because they'd been expecting Mount St. Helens to erupt up, which is sort of the conventional sort of way that volcanoes erupt, which is they blow things up. But Mount St. Helens had really blown more out. And so you can see that excuse me, that its effects were not equally sort of distributed around it, but were located almost entirely, mostly to the north. And so as a consequence, there are a number of sort of distinct disturbance zones that reflected the volcanic processes that had caused them, if you will. And so here's a map that shows some of those. And what you see is, so the bright red is the debris avalanche. That was sort of the first process, that the landslide. All that debris sort of flowed mostly down the North Fork Toutle River Valley, traveling a little bit to the west. It went down about 14 miles, and buried much of the valley under up to 600 feet of debris. So it sort of completely remade the valley with rock and ice and sediment and such. And then the light green and the dark green show the extent of the lateral blast clouds. So these were the clouds that came after the debris avalanche that exploded out. And they traveled up to 17 miles in a linear distance and affected a 234 square mile area. And so the light green here is what sort of became known as the blowdown zone. This was, the clouds had traveled over the land at over 600 miles per hour. And so they knocked over all the trees, all the standing trees just were flattened. And then at the edge of that, you can see the darker green, what's called the scorch zone. So as the clouds, the lateral blast clouds that traveled away, their energy dissipated and they lost some of their force. So they weren't strong enough to knock over the trees, but they were hot enough to kill them, with sort of heat kill them. And so this left a sort of rim on the edge of the lateral blast cloud reach called the scorch zone, or also more evocatively called the zone of standing dead. And then the pink that's in front are the pyroclastic flows, which is all the pumice. And so this was the scorching hot rock. It just shimmered red for days afterwards. And it created a plain, a sort of 6 square mile apron in front of the mountain that now is called the Pumice Plain. And so this, when ecologists first visited the blast area, this is kind of what they confronted. So they weren't allowed to go in for a couple of weeks. There were a lot of search and rescue operations going on. The eruption had killed 57 people, and people were a number of those people had been missing after the eruption. And so the Washington Air National Guard had been searching for them. Geologists had also been quick to return to try to figure out what had happened, since the eruption had actually taken them quite a bit by surprise. And so ecologists weren't allowed to go into the blast area for a couple of weeks afterwards. And so when they did, this is kind of what they confronted. This is an image of the blowdown zone. So you can see it's just this gray, kind of a gray waste, trees just knocked over. It's just a sort of visual chaos. And for them, to fly over the mountain, to fly over scenes like this was really, quite daunting. But for them, it was also really exciting because they were, they were thinking, gosh, kind of what an opportunity. Here's a chance to sort of look and see what happens when all of life is cleared out of a space. It's like an experiment on a grand scale. And so what they anticipated was being able to watch as plants and animals kind of crept back into the blast zone little by little over what they thought would be years and, potentially decades. And there was a lot of sort of a big field of ecological theory about disturbance that they could sort of test in real time, because in the past, a lot of the ways people had looked at how biotic communities responded to disturbance had been through processes of inference. But now this was, you had a real time zero, an eruption, you had everything wiped out. And so, that was sort of what they flew in thinking. And so it was that they landed at a lake about 8 miles away, and one of them hopped out of the helicopter, and what should he see at his feet but a little fireweed chute. And so this is a photo taken a couple of months later after it's had a chance to grow. But he jumped down, this ecologist jumped down, and near his boot was a little 2-inch shoot. And he looked all around, and suddenly he saw that there were lots of little fireweeds growing out of the ash, just like this. And so, it made a certain amount of sense in a way, because fireweed, so this is fireweed when it's blooming. It's a prolific plant. It's very common. It's found all over the world. And it's a classic sort of pioneer species that does really well in disturbed habitats, which is why its common name is fireweed, because it's often one of the first trees to grow back in an area in a forest that's been decimated by forest fire. And so, but the thing about fireweed that was surprising was that this was made, so it wasn't like this plant could have come from a seed. What the ecologists realized was that the plant had to have survived somehow and sprouted from a bit of shoot. And so they returned and they kept watching these patches to see what would happen. And so they realized that fireweed was really perfect for Mount St. Helens, and Mount St. Helens was perfect for fireweed because it grows really quickly. So this is an image of a spot, somewhere in the blowdown zone. This is it a little bit later in the summer when a plot has been set up, and you can see how rapidly it's been sort of populated by fireweed. And then by the end of the summer, when the growing season is done, fireweeds can produce thousands of seeds. And so they spread like crazy. I mean, to gardeners, to see a fireweed show up in your garden is not always a super happy experience, because you realize if you don't want fireweed, you're going to be dealing with a formidable foe. But in Mount St. Helens, they were able to spread far and wide. And it wasn't just fireweed that Jerry Franklin saw when he came out of the helicopter that first time. He also saw some huckleberries growing out of the roots of fallen trees. And here's a picture of curly everlasting growing out of some ash, cracks in the ash. And so this was not what ecologists had expected to find at all. And so they realized that they would have to sort of revise their initial hypotheses, that rather than a sort of decades-long recovery from zero, some places a post-eruption community response would be really, really rapid, and it would be pretty diverse and just full of surprises. And so what they came away thinking was that we really need to study, as much of this as we can, and in as many ways as we can, looking not just at plants, but also animals and soil development and, microbial communities and things like that. And so in part because of their enthusiasm and the efforts of conservationists and ecologists, and also, state and federal government. The Mount St. Helens National Volcanic Monument was created in 1982, and it sort of protected 110,000 acres, most of which is north of the mountain. And it was to be a place for, this is sort of a famous phrase, the geologic forces in ecological succession to continue substantially unimpeded. And so since the founding of the monument, research has covered all sorts of different areas in Mount St. Helens. It's one of the most sort of closely studied landscapes on the planet. And one of the things that was really interesting is in the initial research was in part spurred by the fireweed, is they realized that the post-eruption biological community would have two main influencers, and those were survivors and colonizers. And so the survivors would be the things like the fireweed or the pearly everlasting or huckleberries or some small animals that were able to survive the blast, whether because they were, like the fireweed, able to reproduce from small little bits of root, or like some small mammals and amphibians that they were hibernating actually when the eruption occurred. And so they were shielded in their dens or burrows under several feet of snow, and so were spared the worst effects of the eruption. And then the other thing that would be important would be the colonizers, which would be those organisms that would approach the blast area, repopulate the blast area from outside of it, kind of arrive in waves or individually or something like that. And so in the years since, the two sort of classic organisms have sort of emerged. And one, the classic survivor, is the northern pocket gopher. And the classic colonizer is the prairie lupin. And so the pocket gopher is, you can read about both of these in the book. I have chapters about each, but one of the things that happened while I was reporting it is I was talking to one of the main researchers, and he was like, pocket gophers and prairie lupins. All anybody wants to talk about is pocket gophers and prairie lupins. Please talk about something other than pocket gophers and prairie lupins. And so I promised him that I would, because, I try to I'm agreeable, I guess, like that. And so, as I said, you can read about pocket gophers and prairie lupins and find out all about them. But for the rest of the talk, I want to look at two newer colonizers and survivors, and look at how they tell a slightly different story about Mount St. Helens than the pocket gopher and the prairie lupin. And these are, as the colonizer, the rainbow trout, and as a survivor, the elk. And so these are interesting sort of organisms to me, because I think they illustrate some of the tensions sort of inherent to the monument's aims and purposes, and how the sort of known story of Mount St. Helens of being a place that, where things were wiped clean and life came back fairly quickly, is actually can be pretty complicated. And so I want to start with the rainbow trout. So the rainbow trout, it is a salmonid, like the Pacific salmon. It's in the same family and the same genus. And it's a really popular game fish. It's found all over the world. It's been introduced widely. It's a very common feature in a lot of high mountain lakes. People would bring up rainbow trout and stock the lakes because everybody likes fishing in lakes. And so, but the neat thing about rainbow trout at Mount St. Helens is that the story of the rainbow trout is kind of the story of Spirit Lake. And so Spirit Lake, this is Spirit Lake pre-eruption, pre-1980. And so you can see that it's a pretty typical Pacific Northwest mountain lake, in that it's deep and it was very clear. It didn't have a lot of nutrients, low nutrient levels, so it would be what you would call oligotrophic. And it was also, as you can see, there are a number of boats on it. So it was very popular. It was a very popular recreation destination where people would come up and they'd go canoeing or they'd go sailing. The shore of Spirit Lake in the old days was lined with cabins and lodges and camps. And it was just a real, and of course you had the mountain on your doorstep like that. Very, very popular place to go. And this is what Spirit Lake looked like after the eruption, quite a bit different, as you can see. So Spirit Lake sits a little more than 2 miles north of the volcano. And so it really bore a lot of the brunt of the eruption. And so in the landslide that I talked about, when the summit and the north flank collapsed, they actually collapsed in 3 blocks. And the first block, which was a smaller block, slammed directly into Spirit Lake. And it hit the lake so hard that there's some speculation that for a moment, the basin may have emptied entirely. And so when the water, you can imagine it sloshing up on the surrounding hillsides. And if you go and look at the hillsides today, you can see these sort of scour marks where the water has hit, where the water washed up, and they're several hundred feet high. And so while the first block of debris is slamming into Spirit Lake, the lateral blast cloud is flying over it and, flaying all the trees, so knocking down all the trees. So the water rushes up the hillsides, grabs all these trees, and hauls them back down into the lake. And so you can see in this image what looks like a film is actually hundreds of thousands of tree trunks, of dead trees floating on top of the lake, on the lake surface like a log mat. And it's in the beginning, in the first years, the log mat covered about 40% of the lake surface. But in the years since, the trees, some of them have sunk. And so now the log mat covers about 20% of the lake surface. But it's quite a feature. I mean, you can see it during the day. It kind of moves around, the logs floating. Sometimes they gather up. The wind pushes them into one of the lake arms. Sometimes they're more widely dispersed. It's quite something to see. It's sort of slow motion dance of the logs on the surface of Spirit Lake. And so some other things about Spirit Lake that were changed is that its bottom was raised about 200 feet by all the debris, and its surface area increased from about 1,300 acres to about 2,200 acres, so it almost doubled. And so this is the scene that researchers faced when they arrived at Spirit Lake shortly after the eruption. What they found was this fetid black broth full of logs, covered with ash, full of logs, ash. There's pumice because the pyroclastic flows had rained down on them into the lake. And the water was really, really warm. It was kind of an ideal growth medium for bacteria. And so there was actually some of the researchers working at Spirit Lake fell ill with what they sort of colloquially called red zone fever, but what was later determined to be caused by Legionella bacterium, which are the bacteria that cause Legionnaire's disease. And 2 new species of Legionella were actually found in Spirit Lake, and they were subsequently named Legionella St. Helensi and Legionella spiritensis to commemorate their origins. But the interesting thing about Spirit Lake also is that the dynamics of it were almost completely the opposite of what was happening terrestrially. So even though on land there were survivors that were sort of slowly repopulating these ash, the blowdown zone and the pyroclastic flows, the lake, although absolutely nothing had survived, and of that everyone was certain, the lake just suddenly overflowed with life. And the life tended to be microbial. It was an anaerobic bacteria, chemotrophic bacteria, things that feast on organic matter. And so what this image shows is 2 sort of samples of water samples from the one on the left is August 1980. The one on the right is May 1981. And so you can see in August, the water is just dark with organic debris, organic matter, and life and bacteria. But over the course of the fall and the winter, the lake got sort of cleansed by snowmelt and rainfall, and so that only a year later the water was clear. And phytoplankton and zooplankton, photosynthetic organisms, first came back to the lake. Were found in 1982. And by 1983, the water was back pretty much to what you would think of as kind of normal. And so this is an image of Spirit Lake in 2004, and this is kind of the new Spirit Lake. So it isn't that Spirit Lake went back to being at all what it was like before the eruption. It's actually quite a different lake. For one thing, there are a lot more nutrients in it now. So it went from being nutrient poor or oligotrophic to nutrient richer or eutrophic. And so with more nutrients now, there are more plants, there are a lot more organisms. And so a lot of aquatic invertebrates and insects around the lake that sort of use the lake and the plants now. And so as Spirit Lake cleared, biologists wanted to know what was happening with fish. And so several lakes around Mount St. Helens, in addition to Spirit Lake, had been stocked with fish prior to the eruption. And so Spirit Lake itself had been pretty heavily stocked with rainbow trout since, since the 1930s. And so from the 1930s until 1979, it had state wildlife managers had planted, as they'd say, about 40,000 rainbow trout fry or fingerlings per year in an effort to sort of promote a recreational fishery. And so although all of those fish in Spirit Lake were killed during the eruption, in other lakes, biologists were able to find surviving fish. And so that's what this image shows, is a biologist visiting another backcountry lake. And so what they would do is they would, in 1981 and 1982, they went back and they would helicopter in, they would put out a gill net and they would bait it with usually like canned chicken or sometimes canned tuna, I guess, if they were feeling a little sadistic. And then they would come back the next day and see what they caught. And often they were able to catch fish. They caught a lot of brook trout, and I think there was also some cutthroat. And so the fish, they were never doing very well. They weren't in prime condition, but they had survived. And the way they had survived was that the lakes, especially the higher lakes, in May 1980 were still ice covered. And so the fish survived under the ice. The lateral blast clouds swept over the lake, trees fell on it, but they fell on ice. And so they didn't sort of penetrate. And so when the ice melted and the fish kind of came out and they were still, alive and kicking. And but there was no hope of that in Spirit Lake. And so fish surveys in Spirit Lake tended to be fairly haphazard. I mean, there'd be an occasional survey, somebody would go in and sort of, throw out a net and they wouldn't catch anything. They'd be like, okay, whatever. But then in 1993, state biologists went out and they caught a single male rainbow trout. And they were so surprised because they hadn't been expecting it at all. So this little trout, it was fairly small, but they were thrilled and they named it Harry, after Harry Truman, the cantankerous lodge owner who had lived on Spirit Lake up to the eruption and refused to evacuate, and then was one of the sort of eruption's more famous victims. And then the next year they went back out and they caught another trout. And this one was a female, which they named Harriet. And so they kept returning and kept surveying, and they would catch a few rainbow trouts every year, but not a ton. And then finally in 2002, they went out and this is Bob Lucas and Don Weinheimer, two biologists with the state of Washington. They were out surveying in 2002 in a boat using a hook and line. And Lucas cast his line and this enormous trout leaped out. And as he would say, that was when we knew that Spirit Lake had finally turned a corner. And so you can see laid out in front of him his research catch from a later year. But the thing that they were thrilled about was the rainbow trout of Spirit Lake were enormous. They were, big lunker trout. They were over 2 feet long. They weighed more than 4 pounds. They were some of the largest lake-bound rainbow trout found anywhere in the world. Where the trout had come from was a bit of a mystery. It was assumed that they were introduced by humans. Nobody ever really took responsibility, although there was a lot of sort of rumor and innuendo flying around, in the years later. Where's the trout from? Where's the trout from? People they did genetic surveys of the trout to try to determine their origin, and all they could do was show that they were not local trout. They were not from the pre-existing population. But they were there, and so biologists started to study them as part of the lake system. And so, they wanted to know what they were eating, where they were spawning. And what they found out was that they were making do with a lot of sort of aquatic invertebrates and bugs and things like that. They would sort of scour the bottom, or they would just eat large clumps of the vegetation to get snails and things like that. And what they were also doing, the biologists found, was they're treating Spirit Lake effectively like an ocean. So they would spawn in the nearby streams, and then they would migrate out to Spirit Lake and stay there for a period of time, and then they would migrate back to the streams to spawn. But something else happened. So their populations really exploded because basically they had the lake to themselves. But then something happened, or biologists sort of documented this interesting study or sort of feature, is that as the more trout there were, the smaller they started to get. So even though their overall biomass was pretty constant, there were just smaller fish, and they were losing a constant, they were sort of shrinking at a constant rate, kind of shedding an inch or two of length and a few ounces of weight every year. And so when it became clear that these wonderful big lunker trout were shrinking, state managers wanted to try to open up a recreational fishery on Spirit Lake because there were all these gorgeous fat ID trout. And sometimes the state biologists, when they were doing surveys, they would bring out a volunteer, and the volunteers would go back to their fisher friends and they would say, oh, the fish at Spirit Lake are just something. But it was a tricky sort of management issue, because to fish at Spirit Lake would be quite a bit more dangerous than it would be to fish at most other places. And there were a lot of questions about logistics. So the federal sort of managers, the Forest Service, which is responsible for managing the monument, ultimately said no, but that's still a sort of sticky issue. And it's one of so what this image shows is one of the federal biologists doing what he calls a hook and line sample. When they go out every year and they catch a few Spirit Lake or a few rainbow trouts, and they measure them and then they release them. And for me, I don't know, this is one of the reasons that I think of rainbow trout as a new sort of mascot or exemplar of a colonizer, because where the prairie lupin was sort of explicitly ecological. It was a plant that showed up in the middle of nowhere and nobody knew why, but the trout is quite a bit more complicated. So, they existed in Spirit Lake pre-eruption, but they were introduced and artificially stocked. And then the eruption, the mountain kind of cast them out, but then they were brought back most likely by humans. And so they have become part of the system, but they sort of make that line between what is natural and unnatural a little bit hazy, or they show that it's a permeable line, that you can't just, as much as you would try to with something like a monument where, you can't just draw a line and say nothing, shall happen over here or within here. And so that also kind of leads to a sort of debate about what is the monument for, is it like, how do we sort of use the sort of resources within the monument? And so, yes, and now to talk about what I want to talk about is the new sort of survivor, the elk. And so this is a picture of a bachelor herd of elk on the Pumice Plain. And elk and their ilk didn't fare terribly well in the eruption, as you might imagine, because unlike a pocket gopher or a field mouse or something, they couldn't, bury themselves in the ground to sleep. They were all just above ground. And so biologists kind of call them a large above ground fauna. And in reports I've read, the large above ground fauna did not fare very well. According to a state estimate, 1,500 elk were likely killed during the eruption, along with 5,000 deer, 200 black bears, and some unknown number of cougars and bears, or cougars and bobcats, excuse me. And so because of the, what would you say, the total lack of uncertainty, there's no question that no elk survived. The approach of that scientists took when they were studying elk and their responses to the eruption was a little bit different. So there'd be no search for survivors, but there were still things that you could learn from the dead. And this was one of it was sort of the bodies in their bodiness also contained information. And so this is an image that shows elk skeleton that was dug out of the ash a few miles from the mountain that was presumed to have been killed in the eruption. And so there were a number of skeletons sort of found widely throughout the blast area that in this way, one biologist told me it was a little bit like Pompeii, the city that had been buried by the eruption of Vesuvius. Is they would go and they would find these sort of lumps, and lumps in the ground, and they would dig and they would find an elk skeleton. sometimes they would talk about they would see patches of empty ground, and then in the middle of the ground there'd be just a few plants growing, and they would, somebody would go over and dig, and they would find an elk under that little group of plants. And what it turned out was that the seeds in the elk's gut had germinated and grown where the elk fell. And so another thing that they figured out when they were looking at the skeletons is they could sex them. And in some cases, the female skeletons, they would find another skeleton, which was its calf, or in some cases, a fetus even within the adult female skeleton. And so two biologists initiated a study on elk calving grounds, because this was a source of some management interest, and people wanted to know where female elk were going. And so as sort of a feature of elk natural history, so they formed the herds, the sort of breeding herds. There'll be an adult male, and he'll have a harem of females. But when the females are about to give birth, they separate themselves and they go off to their sort of these private spaces to give birth in isolation. And this is thought to help protect their calves from predators. And so the question was, where do they go? And nobody really knew all that well. And in the old days, in the 1970s and before, what you could do to find an elk or track one remotely was you'd put a radio collar on it, and then you'd follow that around. But that was a fairly, iffy proposition. And so what biologists did after Mount St. Helens was like, well, we could radio collar these elk, or we could just wait for the volcano to kill them all and then go find them. And so that was what they did. And so what they ended up doing was mapping the skeletons where they lay, and they noted which were females with calves and then they were able to determine which meadows were more likely to be used. And so this is where a lot of those elk skeletons ended up. This is an off-site storage facility of the Burke Museum of Natural History at the University of Washington. And in each of those boxes is 1 or 2 or up to 4 elk remains, sometimes males, sometimes females, sometimes calves. And you can see it's a fairly decent number. There's several, I think, counted once, there's several hundred, or, I should say several dozen, I think, skeletons sort of within the collection that were used for the study. And which is a point in itself, because while 1,500 dead elk might sound like a lot of elk, the Mount St. Helens herd, which is the herd that they're sort of officially a part of, was made up of up to 10,000 elk. So 8,500 elk, at least, sort of survived the blast within the sort of Mount St. Helens area, sort of region. And this is an image showing from 1983, showing some elk exploring the blast area. And so many elk survived just outside the blast area. One biologist I talked to spoke of seeing elk on hillsides surrounding them, and she would look more closely and she would see these kind of twitching nubs on their heads that she realized were where their ears had been before they'd been burned off by the end of the lateral blast cloud. And so, but the elk were some of the first creatures to return to the blast area of their own accord. I mean, they're highly mobile and they're large. They can travel pretty far in a day. And so their initial forays into the blast area were usually pretty brief. They would go in a few hundred yards or so, and then they would kind of retreat to more hospitable habitats. But eventually they became more of a constant presence in the blast area. And part of the thing is they were drawn there by plants like fireweed, which were growing up very well. And so they would use this as sort of summer forage. And one biologist called fireweed, she said it was elk ice cream. It's very, rich and they love it. And so they would go in and eat it. And then in the winter, they could eat grass and seeds that had been planted in some areas as to help with erosion control. And so their rebound was quite swift. as large mammals go. So they went in 1981, there were about 200 elk known to be wandering around the blast area. And then by 1985, there were more than 600. And so this is a picture of a mixed herd just sort of wandering around in the debris avalanche. And so they would range all over the place in the debris avalanche and the blowdown zone. They even made it to the pumice plains. And they were a real sort of agent of dispersal for plants. And in the beginning, so they were quite good for plants. So this is a picture of some prairie lupins growing amongst some elk droppings. And so each sort of, pellet of elk poop was an effective little prill of fertilizer, if you will. So they would walk around, they would poop everywhere. Their poop contained seeds, so they were dispersal agents. The poop itself was a fertilizer to sort of add nutrients to what was largely nutrient poor soils, or not even soils, but like ash. They started to sort of help plants return to the blast area. And the other thing, and they would carry seeds in their fur. And the other thing they would do is they would, with their sharp hooves, they could break up the ash and the pumice. So when the ash, it would get rained on, and then it would get baked, and then it would get really, really hard. And so it was really difficult for plant seeds to penetrate that as a substance. But then an elk would walk through and stomp it all up, and it would, and then suddenly a plant might be able to germinate. And if it was like a prairie lupin, which has a very tough, hardy root, it could send that root down into old soils perhaps, or find water. And so the elk were really, real agents of dispersal, if you will. I mean, really helping things out. But their success came at a kind of cost. So as the elk numbers increased in the blast area, they began to run up against the blast area's carrying capacity. And so they were running out of food. And then they would start to starve in the winters. And so the Washington Department of Fish and Wildlife began to survey in 1999 to find how many elk were starving. And they would find that within the Mount St. Helens area, up to 150 elk might starve over the course of a winter. And so starving elk in the blast area were not something that people in the communities outside the monument really liked to see. It was pretty upsetting. And there would be stories in local papers about the starving elk, and they would show elk kind of, very emaciated, struggling to stand, things like that. And there was a bit of a public outcry. And so because of that, state managers began to provide supplemental feedings for the elk. So they would bring hay up from Oregon or Eastern Washington, and they would create these sort of hay depots, and the elk would show up and eat and hopefully sort of persist. And that's still sort of an issue. In 2019, the Rocky Mountain Elk Foundation gave about $300,000 for elk habitat enhancement around Mount St. Helens. And so as, whether through sort of a natural culling or the supplemental feeding, the elk herd has pretty much stabilized. And so this has led to a kind of change in their successional influence, if you will, where they've gone from being a largely positive force to one that is mixed kind of at best. And so this image shows a conifer tree, a young conifer growing in the debris avalanche area. And so trees within the sort of successional matrix usually are the last thing to arrive. And so throughout the blast area now, if you go, you'll see a lot of these sort of short trees that are starting to grow. And a lot of them look like this. This one has been very heavily browsed by elk. You can see the top of it is more sort of conventionally tree-like, but the middle and the base is eaten down. And so the elk would go through and they would eat almost all the new growth on the trees. And so, and then also as they were walking, now where before their steps had been to break up the ash and make it more sort of, welcoming to plants, now they're actually stepping on plants. And so they create these sort of game trails and they stomp on the new vegetation. And so for the biologists, the monument biologists, there's this real kind of question about elk of whether they are as one of them said to me, he was like, well, an elk walks through a study plot and it sets succession back 10 years. It stomps on all the plants. It really sort of interrupts succession. And so is this sort of, as he was saying, is this succession that's being impeded? And so because of that, they decided to step in to try to sort of lessen the effect of elk in the blast area. And so in 2005, the monument biologists advocated for a hunt in the blast area. And this wasn't the first time that this had happened. In 1982, they held a hunt of elk as their numbers were starting to rise around the edges of the blast area in the lateral blast in the blowdown zone. And ironically, it was that hunt that drove elk into the heart of the blast area around the pumice plains and places like that, because hunting in the monument wasn't allowed. And so the elk knew a safe refuge when they saw one, and so they just kind of all moved in to where they couldn't be shot, and then that was when their successional influence really started to change. So in 2005, in an effort to kind of reverse that, they advocated for a hunt in that area, in the heart of the blast area, to try to compel the elk to move out. It didn't quite work out that way. The federal managers said no to the hunt inside the blast area, but they were in the heart of the blast area, but they allowed one that's still on kind of the fringe. And so you can hunt elk, but the elk still have free reign of the pumice plain. And so they've continued to stay there. And it was one of those sort of unintended consequences of advocating for a hunt. And so this, I don't know, this is, for me, is what makes elk kind of the new mascot of the survivor, of again showing how complicated a space Mount St. Helens can be, because they put a real sort of pressure on the phrase of ecological succession substantially unimpeded. Because the question is then, unimpeded by whom? Because elk are, more so than the rainbow trout, elk are very much a natural part of the landscape. They left, when they came back, they did so entirely unaided. And then later, when people stepped in to try to help them, that led other people to be unhappy about how they were doing. But elk, in that way, they just show how Mount St. Helens and the blast area will always be a sort of beautiful and complex space, you can't look at it and only draw one thing away. It seems you have to sort of embrace various contradictions and sort of dueling ideals, I guess, if you will. And so I want to close with an image of Mount St. Helens that shows a time lapse from NASA satellites from 1979 to 2016. And sort of to think about what Mount St. Helens teaches us, or to show what's new. And I mean, sort of the lessons that I've taken away from exploring Mount St. Helens for the past several years is that you learn that things will always come back, and that life is resilient, even if the communities that come back are very different from the ones that started. But that sense of resilience in the face of unfathomable disasters really is quite interesting and inspiring in a way. And even if it doesn't come back as you expect it, or even, it will always be full of surprises. And as you watch, people expected that this green would take forever to come back, but slowly, but very persistently, the green is filling up what was once a very, very gray waste. And so thank you very much. I hope you've enjoyed it. I'm very happy to take questions now or hear stories about what you remember from the eruption, or having been to the blast area now, or what your impressions are. And yes, I hope you enjoy it. And again, thank you for joining us.
Hi, I hope that you can all see me and hear me. I see that, so throughout, I've been getting some questions, and I've been writing some of them down, and so now I will try to answer them. I can see some others are coming in, so I'll just get started. And if you have any other, if things come up while I'm talking, free to ask them, and I will try to get to them. Okay, so the first question that somebody asked was, could trout have come from streams feeding the lake? And the answer is probably not. So most of the watershed feeding Spirit Lake was pretty significantly disturbed. I mean, we say disturbed, but in a sort of looser parlance, you'd be like, oh, it was just totally destroyed. And so there's one thought that perhaps there's a St. Helens Lake, it's a lake a little bit higher behind Spirit Lake with some that are thought to perhaps have some trout in them, but there's no real sort of way for the trout to get there. There is a sort of alternate or kind of pet theory among biologists that maybe some steelhead, which are sort of genetic, both rainbow trout and steelhead are the same species, Oncorhynchus micus, but steelhead is the seagoing form of the rainbow trout. So the rainbow trout lives in freshwater and spends all of its life in freshwater, and steelhead, like the other Pacific salmon, start out in freshwater and migrate out to the sea and then come back. And there have been some sort of questions of whether or not the North Fork Toutle River reconnected temporarily with Spirit Lake at some point in the mid-90s. And so maybe a steelhead snuck in, and that might have been the source of the rainbow trout. But if we're playing with likelihoods, the chances are, given the sort of history and practice of stocking, that somebody put trout in the lake artificially. So the next question somebody asked was, what are other surprising things that I learned? So many, it's hard to know what to talk about. They're just it's this place that's just full of surprises. One of my favorite stories that I heard was, so there's this tiny frog, the Pacific chorus frog or the Pacific tree frog, which the adults are maybe an inch long, bright green. And a biologist who has spent most of his career in the blast area found a Pacific tree frog up in the crater of Mount St. Helens. And so the nearest source population was something like 5 miles away. So somehow this little tiny frog had hopped 5 miles along sort of stream beds and things to end up in the crater of Mount St. Helens, where this biologist just sort of found it, living nice as you please. And so that was a pretty delightful thing to see. Let me actually, so that you're not just seeing a blank screen, share, see if I can share that at least. Okay, so I'm not sure if you're seeing the questions too. Anyway, so, it's all right. Okay. Another question was, how did small animals manage to adapt to the wasteland they emerged into? And so this would be things like the pocket gopher, or there are a whole bunch actually. I mean, some western toads were another one. And so the answer is, so in the case of pocket gophers, they were able to sort of continue to survive on the roots of plants that were buried. And so that gave them a bit of a store to live on until other plants came back. But one of the things that's sort of interesting in talking about sort of species holistically like that, like you say, oh, the pocket gopher, and that's sort of meant to, taken to mean this sort of totalizing pocket gopher. But a lot of pocket gophers probably died. Some of them survived, some of them didn't. A lot of it was real sort of luck of the draw. And so, some, like, and the same would be true with western toads. Like, some would do well and some would not. And so, yeah, that was how they were able to do that. Sorry, I have to go back and read the questions so I can see the questions. So another question is, can you tell us more about how scientists who've studied the area for years talk about their work? What have they gained from it? How do they feel about it? So they feel very strongly about it. I mean, in many cases, especially for the people who worked there from the beginning, it was such a shock. You know, nobody who was there, among the original researchers, planned to study volcanoes. Many of them came from forestry or other sort of fields of biology, and then suddenly this volcano erupts in south central Washington, and they go rushing up there, and then they end up staying there for years and years and years. And so there's a real, that sort of sense of awe of, of luck, serendipity that sort of put them in this amazing place at this amazing time to ask these amazing questions. And so even the scientists who maybe stayed for 5 years or 10 years and then went on to do other things, they still feel this real sort of sense of connection with the mountain. And there's this really cool event, and I talk about it a little bit in the book, called a pulse. And so every 5 years, scientists, they come together and gather in the summer at Mount St. Helens, upward of 100 or so researchers who've either worked there or are working there. And they go and they gather data from old plots to sort of keep studies going. They bandy around ideas for new studies. They sort of try to usher in younger researchers to, sort of continue the research tradition, the ecological research tradition at Mount St. Helens. And so there's this real sense of stewardship that comes, it seems, from working there. And it's really interesting to see. So another question is, so was the study of recovery mainly a local effort, or were there scientists there from other parts of the world? And have people been able to do comparative work in other places? That's a great question. So a lot of the research, the scientists who came there first were from the Pacific Northwest. There was a large team that had sort of gathered from the Andrews Forest down in Oregon, in Central Oregon. Now, the Andrews is a research forest that's sort of supervised or overseen by the Forest Service and Oregon State University. And so the original sort of team started there, and then they migrated up to Washington to work. And there were also a lot of researchers from the University of Washington, as you would expect. There were people from across the West. But in recent years, there have been more sort of international collaborations. And so the neat thing, so the bit about the question, have people been able to do comparative work in other places? So one of the coolest things is that there's a team from Mount St. Helens that has been going to Chile for the past, I want to say, almost 10 years now, because Chile is very sort of volcanically similar to the Pacific Northwest. And there's a chapter, I talk about it in the book. There was an eruption of, it's called Volcan Calbuco in 2015 in Chile, and there are actually 3 eruptions. So there was one in 2009, I think another in 2012, and then this last one in 2015. And biologists and ecologists from Mount St. Helens went down to Chile to sort of collaborate with Chilean biologists to set up similar types of studies that they've set up at Mount St. Helens, which is to say long-term ecological research and monitoring. And so it's been really cool. And I know that the folks from Mount St. Helens really enjoy that sort of sense of exchange that's come from being able to work with on Chilean volcanoes. So another question is, are there any species that didn't survive the blast? That's a good question. There are, so, excuse me. Offhand, I can't think of any that just were completely eradicated, so much so that they haven't returned. I mean, in the sense of, there were some type of, say, a bobcat, and then it never came back. There are, with the plants, there are things that are just starting to come back fairly recently, like trees in certain parts of the blast area, given the sort of successional dynamics. So, but nothing that I can think of that has been sort of totally removed. So another question: was there any wolf predation on the elk? Now that's a good question. That's kind of a loaded question. There are no elk, or no wolves, excuse me, there are plenty of elk. There are no wolves in Southwest Washington, or no wolf packs. I think none south of Interstate 90. And, but one of the biologists, so who's the one who was busy sort of trying to instigate the hunt, has said that what the blast area really needs is wolves, because that would be a great area for them. It's a lot of open land. There isn't a lot of, there isn't comparatively as much ranching, cattle ranching, as there is in the northeastern part of the state, which is how you end up with a lot of sort of wolf livestock conflicts. And it's, so Mount St. Helens is right next to the Dark Divide, which is one of the largest roadless areas, I think, in the state. And so wolves, if they came back, he's really hoping, the biologist is really hoping that they get back fairly soon, because then that would do a lot to, restore a kind of older ecological equilibrium between the elk and the plants in the blast area. So another question is, how do scientists decide when to intervene in the recovery of what they're studying and when not to? That's a tricky one. I spend a lot of the book not a lot of it, but I definitely tackle that question in the book. And I think, because it's a really interesting one for me, because, the whole point of Mount St. Helens is supposed to be that it's ecological succession substantially unimpeded. But what about if it's sort of assisted? And I don't know. I think in the case of the elk is really interesting because it's almost like, there's, I don't know, I don't want to put words in this person's mouth, but it's almost like there's a kind of irritation at the elk for being so prevalent. And that is kind of what prompts us the desire for a management intervention. But yeah, so I don't know if there's definitely no sort of set protocol that I know of. But yeah, that's a tough question that they're still sort of dealing with. Let's see. So now I'm going to go. Okay. So here's a question. What about salmon recolonization in the Toutle? Tell us what happened there. Well, I have a chapter about it in the book, about steelhead and their return, and coho as well. And so it's pretty interesting to watch because the North Fork Toutle had one of the most productive steelhead runs pre-eruption. And then afterwards, it was filled, the river was just buried, and filled with silt. And this was another sort of massive intervention on the part of people, because one of the things that they're really worried about is all of the silt washing down to the lower, to the Cowlitz River and the Columbia. And because when the eruption happened in the 1980 eruption, there were these huge mud flows that were really destructive. And they ended up reaching all the way to the Columbia, where they clogged the shipping lane. They shrunk the shipping lanes from a depth of, I think it was 40 feet up to 13 feet. And then the Army Corps of Engineers had to spend months frantically digging that out. And so they're very, very sensitive about that happening again. So as a consequence, they put a sediment retention dam about 20 miles from the mountain, and that holds a lot of the sediment back, so it just sort of trickles out little by little, but even then you still have to do a fair amount of dredging. So as a consequence, the Toutle, at the sediment retention dam, there's what's called a fish collection facility, where any steelhead, which in that part of the state are listed as threatened under the Endangered Species Act, any steelhead that makes it that far is captured and then trucked up to one of the old creeks, the Hofstadt Creek or Bear Creek. These are Hofstadt is on the north side of the Toutle, and the Bear Creek, I think, is on the south side. So the numbers there are still fairly low. I think they're getting 88 to 200 fish perhaps a year. The management goal is to get 600 fish, and if 600 returning spawners, and they're not really close to that. It's a very difficult environment for fish, because of all the silt, because the silt abrades their lungs. The water quality is pretty bad until they get to the creeks, and then it clears out, and then it sounds like they do okay. So salmon recovery is continuing slowly on the Toutle. The South Fork Toutle, which didn't receive much effect. There was a mud flow, but not anything like the debris avalanche, is actually doing a lot better, or salmon there are. So somebody asks, you said that fishing in Spirit Lake is dangerous. Why is that? And so one of the reasons, the reason it's dangerous is if you were to take a boat onto Spirit Lake, there's a real risk of getting caught in the log mat. So the Spirit Lake, as I mentioned, is covered with still, thousands and thousands of logs. And with some of the researchers, I went boating around on it once, and it's really quite something to watch the logs move. They move very subtly and sneakily, and then suddenly you'll be looking around, and the way that you came, there's a whole bunch of these enormous logs floating across it, and you'd have to try to pick your way out. You could probably, I don't know. So that's the main reason. The other reason is that in order to reach Spirit Lake, you'd have to really sort of fortify a lot of the blast area. There's currently, I think, one trail to it that's about a mile long. It's pretty steep. And yeah, so the main concern is that people would try to get out on boats, and then they'd get in trouble, and then there'd be a lot of having to pluck people out of danger. Let's see. So, what were the predators of the elk prior to the blast, and why haven't those predators returned? So the main predators, I don't know if there were too many. There would be cougars potentially, and those are back, but cougars don't have a significant enough effect. The main predator, as I think I mentioned earlier, was the wolf, and that's sort of what they're waiting. What they would, in an ideal world, that wolves would come back, and then they would be able to predate the elk. Let's see. What about frogs, salamanders, and the rest of the lovely amphibian tribe? Well, they are doing pretty well. So there are a couple of areas. So amphibians were one of the sort of surprises. I mentioned a little bit earlier the western toad, and I talk a little bit about the western toad in the book as being one of the real sort of shockers. So I'll tell a brief sort of story of the western toad. So the western toad is threatened throughout much of its range, and it was present at Mount St. Helens before the eruption, but not in any sort of great numbers. And then after the eruption, their numbers just exploded. So in part, the eruption created a lot of really toad-friendly habitat. So toads like open, sunny spaces, and so suddenly, there were hundreds of square miles where there weren't any trees, and so the toads would, they had survived in their winter burrows. They emerged and hopped out, and all of their predators were gone. All of their above ground sort of snakes and things had been killed, and so they just had run of the place. And so biologists documented toad densities, the likes of which had never been seen anywhere. And I don't know if anybody has ever seen a spawning, or not a spawning, but a western toad sort of toadlet emergence, which happens in July in the summer. And so, they lay thousands and thousands of eggs, and then all these little toadlets emerge and hop up onto the lake shores. And if you go and you look, it's just a teeming mass of these tiny, tiny little toads, which are, maybe half an inch long or so. And it's quite a thing to see. One of the things, though, that's interesting is, so while the toads, they did very well initially, but now that in the parts where they're doing very well, the forest is coming back, the canopy is closing a little bit, sort of depriving them of their preferred sunny spots. And so their numbers are declining a little down to, they're still doing well, but they're not doing as fantastically as they were before. Let's see. So, have there been any studies comparing forest fire impacts to the effects of Mount St. Helens? That's a good question. None that I know of in a one-to-one sort of way. One of the things that's interesting with Mount St. Helens is how it's kind of fit into the larger literature of what are known as large infrequent disturbances. And so forest fires are considered something like that. Although we see them a lot, in a sort of broad regional sense, but on a sort of spot by spot basis, they're considered large and infrequent. And so there's a series of studies, I want to say it's from the early 2000s, where researchers looked at, sort of compared the effects of Mount St. Helens, the big Yellowstone fires in the late 90s, and then hurricanes in the Caribbean. And so they looked at sort of the ecological ramifications of these large infrequent disturbances and how different organisms or different communities are sort of subject to these, how they respond to getting slammed by a hurricane, every 2 or 3 years, to how they, these century-old fires, and ways that you can sort of see the evidence of these things in the community. So anyway, while I can't think of a comparative study in that sense, although it may exist, it's been interesting to learn how Mount St. Helens fits within the larger framework of disturbance studies. So, what was the strangest, least expected plant to come back, and how about opportunistic invasives versus native species? So I mentioned the colonizer, the sort of classic colonizer species is the prairie lupin. And I talk about it in the book, so I'll talk a little bit about it now. But so that was the first species to be found on the pumice plain. And that was not a species that anybody expected would show up there first. So lupins, they're very hardy. They have a thick root, a deep woody root. So in that way, they're very tough, but they're very poor dispersers. And what that means is that they don't have the sort of light, fluffy seeds like the fireweed does. They have a heavy, sort of almost like a little lentil that when they release it, they kind of cast it out. And so it doesn't travel very far. And so biologists were in the middle of the pumice plain in I think it was 1981. And they were just walking through this, flat, empty waste, and they see this little kind of purple flower popped up in the middle of nowhere. And it's, so there were a lot of things about the lupins where their ecology did not make them very well suited, or, it wouldn't be a sort of species you would expect. Their natural history was actually turned out to be very well suited to the pumice plain. They completely took it over in the first few years, and it was really, I guess, quite something to see, of like this grayness turning into great purple waves of little lupins. And so as for opportunistic invasives versus native species, so one of the things that was pretty interesting, the available species pool for Mount St. Helens included both native species and non-native species. And so there was certainly sort of a mix. But there was also, one of the things that's interesting is that native or non-native species didn't have the usual kind of avenues to enter, which are usually things like roads. And so native species actually, they were doing pretty well. Now there were a few instances where, and I talk about this. I talk about this in the book, where managers, they wanted to control erosion. So in the parts of the debris avalanche on the western side of the blast area, as the North Fork of the Toutle was kind of starting up again, it was eating away at tons of this sediment, and there was a fear of mud flows and that I talked about earlier. And so what the Soil Conservation Service was what it was called at the time, they dumped tons and tons of plant seeds on the debris avalanche in the hope of stabilizing it. And so the plant seeds that they used were what they would typically use on highways, like on verges, they plant fescue and stuff like that, different types of grass. Excuse me, let me take a quick. And so they flew helicopters over the debris avalanche deposits, and they were scattering seed everywhere. And so one of the sort of interesting, the researchers who are working there were horrified. They're like, what are you doing? We're trying to sort of watch this come back. Could you at least use native seed that is at least from this area? And they were like, no, we got to hurry. But now, kind of as a result of that, one of the sort of legacies of the research at Mount St. Helens is that they're now greenhouses that have regionally appropriate seeds that they use for verges and things like that. So let's see. Question: why have no predators moved in to balance the elk? Well, that's the answer to that is people. We typically, let's see. Humans extirpated most of the predators that would control elk, and now that's sort of why, in the absence of the predators that you would have, like wolves, the biologists asked for a hunt to be opened. So to ask humans to be sort of surrogate, predators in a highly controlled fashion. Yeah. So let's see. Yeah. Oh, here's a question. What was I doing and how did I react when Mount St. Helens erupted? I was 2. I grew up in Astoria, Oregon, which is, I don't know how far, quite a way. You can see Mount St. Helens from Astoria on a very clear day if you're in a high enough spot. But I have, sadly, no memory of the eruption, although I was told that it was quite a thing to see the ash plume billowing up out of the horizon, although all the ash was carried east, and so Astoria was fine. Let's see. So this is a geology question, but I'll take a bit of a stab at it. So how much of the crater has filled in during the last 40 years, and is there continual seismic activity? Yes, there is continual seismic activity. I think Mount St. Helens is being sort of regularly shook and, jostled, as are, lots of places throughout the Pacific Northwest. There was so the crater is refilling. There's a new dome building. There was the big series of eruptions, or what's called a single eruption. I'll take a little tangent. So one of the things that's interesting about the 1980 eruption is that it's actually considered to have been a continuous event for 6 years. So from the first seismic activity in March of 1980 until 1986 is considered, geologically to be a single eruption. And so in 2004, I don't know if people around here remember, there was another eruption that lasted for 4 years, from 2004 through 2008, which was a dome building eruption. So that was just sort of, volcanic product extruding from the vent to rebuild the dome. And so I think that the dome now the new dome that's kind of filling in the crater is something like, it's 1,000 feet tall, I think. And so it's on its way up, soon it will refill, and in, I don't know, 10,000 years or so, maybe we'll have another nice Fuji of North America. So here's a question. What non-human predators are in Mount St. Helens, in the Mount St. Helens National Monument? What do you expect to happen if wolves repopulate the area? So the non-human predators are they're cougars and black bears and bobcats and things like that. Those are sort of the charismatic megafauna and mesofauna. And the cougars are interesting. A couple of years ago, there was a cougar that was actually stalking hikers in the blast area that had people kind of nervous. And then what do you expect to happen if wolves repopulate the area? Well, the hope is that, I mean, and bear in mind that this is probably, at least a decade away before wolves even reach it. I mean, they have to get across I-90 and then work their way down through some pretty populated areas before they'd reach Mount St. Helens. But the thought is that when they get there, they'll have all these elk kind of at their disposal, and then they would they would work to control that portion of the herd. But who knows? There are also some livestock down there, and so I think you could expect a lot of the same sort of conflicts that you have elsewhere in the state. So a question, do you know if citizen science has been recognized and shared with the body of recovery information? So as far as citizen science goes, I know that the Mount St. Helens Institute does a lot of programs that go out and sort of collect data. And so I think there's definitely a sort of citizen science element of that. I can speak as one who, when I was out a couple of years ago, I got the first documented sighting of a black-throated blue warbler in Skamania County. So that is a sort of citizen science element. But so citizen science is included in that, and they're definitely, sort of select avenues of entry. I don't know of any large-scale sort of citizen science project on the order of something like the Coastal Observation and Seabird Survey Team or things like that. Let's see. So here's a question. So how will it look 40 years from now? When will forests return? So the forest is starting to return now to parts of the blast. I mean, so in the blowdown zone, so this is one of the things where you have to look at all the different disturbance zones and you see these sort of different dynamics. So in the blowdown zone, there were young trees that were sort of trapped under the snowpack. There were places that trees survived, young enough trees. And so the forest there, I mean, you can go to like Mead Lake or other places and you'll see trees growing. It's a young forest, but it's still a forest. They're all, the trees are all probably about 40, 42 years old, things like that. There are other parts of the blast area that were pretty significantly replanted by the U.S. Forest Service and private companies like Weyerhaeuser after the eruption, and so those are always kind of a hoot to see and compare to other parts where you go and you see a few scattered trees here and there, and then you cross into an area where there was significant replanting, and it's like all these trees that are exactly 39 years old, and they're all silver fir, and they're all really close to each other, and they're all the exact same height. But the most interesting part where forests returning will be the pumice plain, which is where they're starting to document the trees coming back. And so you can see, this sort of slow march, I guess, of trees kind of coming up. So I should also say that there are some streams in the pumice plain that are just thick with willows. So there are patches where you really have to fight through some trees. but yeah, the forest is starting to come back. And a sort of curious thing about Mount St. Helens is that the tree line was always was lower there than would be expected compared to other Pacific Northwest volcanoes. And so I think one of the theories behind that is because of the eruptive activity, because trees are always getting sort of mowed down and then they have to come back and then they get mowed down again and they have to come back. And so that's what's kept the forest from rising as high up the volcano as they used to. Here's a question. The satellite views of Spirit Lake showed its shape changed a great deal. So actually the changing shape is kind of a quirk of the log mat, which covers so much of the surface that it can make it look like the lake is sort of shrinking and expanding and shrinking and expanding. But actually the lake's sort of overall shape has stayed pretty consistent since the 1980 eruption. So here's a question. What do you think the Legionella bacteria role might be in the Spirit Lake ecosystem? I think it's fairly minimal in that I don't think they've been detected there for quite a few years. And so they really had thrived in the early years when the lake was really warm, when it was really warm and full of organic debris and things like that. And then they kind of got replaced by your more sort of standard suite of phytoplankton, zooplankton, and that type of microbial life. Let's see. Excuse me. Can I talk about how the ecological story benefited and or suffered because of the timing of the blast when snow was still on the ground versus occurring in, say, the summer when the ground was snow-free? And that's a good question. So yes, snow was had a really significant effect on how different areas of the blast, how different sort of zones of the blast area recovered. So for instance, in the blowdown zone, snow was really a savior because trees were buried under the snowpack. Animals were hibernating under there, or they had little tunnels under there, and so they were protected. And then after the eruption and the snow melted away, the young trees sprang back up, the animals emerged, and life continued anew in these rather radically changed circumstances. In other parts of the blast area, like what's called the tephra fall zone or the tephra zone, which is the part that's farthest away from the mountain, where the only volcanic process that affected it was the ash plume. So when the ash plume goes up, it carries west, and carries east, excuse me, and as it's going, it's sort of shedding ash and tephra. Tephra is kind of the word that people use for anything a volcano ejects. So in this case, when I say tephra, usually what I mean is ash. So several inches of ash, or foot or more, falls on mostly, actually, I think it was just several inches, like up to about 8 inches or so on these trees. And it falls on snow on the ground. And then what happened is there was so much, as the snow melted and as it rained, the ash hardened it became like concrete. And so as the snow melts, the ash sort of slab that's sitting on top of it kind of lowers down with it and settles onto the plants that otherwise would be springing up. And so instead of snow being a benefit in the ash fall zone, in the tephra fall zone, it was a real killer. Like places that didn't have snow, their plants responded a lot more quickly than places that did have snow. And then also the main thing that would have happened is if there hadn't been snow, if small animals had been out and about, there would have been almost no survivors of small mammals or amphibians or things like that. So the effects of snow were they're varied and they're wide, and they're diverse, like on both plants and animals, and then whether it was close to or whether it was in the blowdown zone or the tephra fall zone. Here's a, how long will it take for ecological succession to become complete? Which is kind of a trick question because it should never be complete. Like everything you see is sort of a step in succession. I have a fairly extended discussion in the book that I will spare you here about how people used to think of succession of arriving, plants would march through these very defined communities until they reached what's called a climax community, versus thinking of succession as, much more kind of contingent and less goal-oriented, if you will. The other thing is, and the point of Mount St. Helens in a way is that succession often gets sort of reset by large disturbances. And so it's hard to know, maybe Mount St. Helens will erupt again at some point. The first one took people by surprise. Maybe it will happen again, and then succession will start again from zero in some places and with a lot fewer species than others. And so, so the thing is, the point is that ecological succession will probably never be complete, which is why it is so wonderful. So yes, a question, do you think there should be intervention or should recovery happen on its own? Pros and cons. What are the pros and cons of that? In an ideal world, which we very clearly are not living in right now, intervention or recovery or response, this is also a little curio, is they almost never say recovery there, because since recovery presumes a kind of end, or but they say response. What is the biological response? Ideally, the response would happen mostly on its own, but practically that's been pretty impossible. Even in the monument, there's a big thing right now where the Forest Service wants to do some drilling in a part of the, some geotechnical drilling in a part of the debris avalanche to just sort of characterize it. And the Army Corps of Engineers wants to replace a gate on Spirit Lake. And so there's a proposal to build a road across the pumice plain, which the researchers are very unhappy about, because it would significantly affect a lot of their studies. And so there's always this sort of public safety proviso of, well, you can study stuff, but if there's some sort of imminent threat, then people will intervene. In the book I talk about, so one of the things actually with Spirit Lake is Spirit Lake when the eruption, what happened was the debris avalanche cut off Spirit Lake's only outlet. So Spirit Lake used to empty into the North Fork Toutle before 600 feet of mountaintop came and buried that outlet. And so the lake, so the lake started to rise because it was in a closed basin. And in 1983, 1984, the Army Corps of Engineers and the U.S. Forest Service were like, oh my goodness, we can't, the lake, if it breaches the debris dam that's blocking it, it will flood, it'll sort of, and send another devastating mud flow down on Cowlitz and the Toutle, the communities on the Cowlitz and Toutle rivers. And so they drilled a tunnel under a ridge to, the tunnel is 1.6 miles long to let it empty into a creek. And so that was, that's a real intervention, and that's an intervention that had to happen so that the lake wouldn't breach, but also an intervention that's led to a lot of sort of consternation in the research community and among the Forest Service managers, sort of asking, another sort of instance of asking what the monument is for, and how you balance all of these competing aims of research and public safety and recreation and things like that. So somebody asks, I'm being told there are 3 minutes left, and I was told that about a minute ago. So
Eric, it's up to you. You can pick your questions as you want.
Okay. I'm happy to keep going down in, I guess, until we run out of time. Let's see. So do you cover the issue of spiders floating in? I do. That was one of the also delightful things, was learning about how spiders and insects showed up in the blast area just within hours of the eruption. Like rescue crews who were flying looking for hikers and loggers who were missing in the blast area reported seeing spiders and yellow jackets, buzzing around. I talk about it in the book, and it's really that was actually, yes, definitely one of the most delightful things about it, was the sort of realization that came to people that typically you think of biological communities starting with plants, but in the case of the pumice plain, there were reproducing populations of beetles and before plants had widely established at all. And so the beetles and spiders, some of them were sort of subsisting as scavengers because there were so many spiders coming in, spiders and organic material and flies that were, sort of drifting down onto the pumice plains. And it was a very sort of still a very hostile environment. So many of them died. And then these beetles showed up and they were scavengers. And so they'd scavenge all the bodies of these bugs. And there were enough, things for them to eat that they were able to breed. And so, yes, spiders are great and an important part of the Mount St. Helens recovery story. So here's a question. Where do you see a need for more ecological study in the Mount St. Helens area? What research questions or projects did the scientists I interacted with suggest need more attention? So one of the new sort of research projects that was just getting off the ground was a study of stream development in the pumice plain. So because the pyroclastic flows buried all these drainages, these former waterways under up to like 120 feet or so of pumice, the springs in the mountain, they began to sort of eat their way through the pumice eventually. And so now there are these, I think it's 5 streams sort of that go through the pumice plain that with names like, actually, I think one like geothermal stream, Willow Creek, things like that. Those are their names. So it's one of the few areas in the world, I think the only area where scientists can watch streams develop, like streams evolve. And so one of the neat things is all the streams are all different, even though they're very close to each other and occupy the same sorts of areas, they have different temperatures and different slopes and different, different things live in them. And so that's one of the areas that people are really excited about. They're also, one of the things that's neat is seeing people apply new tools to older questions. And so one of the people who's been working at Mount St. Helens for, since the beginning is now going back. He's using LIDAR, that sort of imaging satellite to look at ponds in the hummocks area of the debris avalanche, to look at how their seasonal risings and fallings, so some of them fill with rain, some of them are perennial, how their risings and fallings in this sort of matrix affect amphibian populations and aquatic insects. So let's see. Where were the large trout in Spirit Lake safe to eat? How about fish caught today? So the trout are safe to eat, but nobody can eat them. Nobody is eating them. So I think they would be safe to eat if eating them were allowed, which it is not. So here's a question. So given the success of the prairie lupins have had at adapting to the pumice plain, what factors kept it out in the first place? Probably, I mean, I would guess it was competitive exclusion. So there was an existing sort of community there. It was it was a forest, and so there was no room for them. It was not the sort of place where they would grow, since they're prairie lupins and they're more sort of suited to wide open habitats. And so that was one of the things that made their arrival such a delight, was that this plant that nobody wouldn't think to look for there, because prior to the eruption it had been a forest. Suddenly this prairie lupin shows up. So somebody asks, which mountain in the Cascades do you think is ready to erupt next? I don't know. I would guess probably Mount St. Helens, because that's the one that has been the most lively. Somebody asks, is there any talk of introducing grizzlies into Mount St. Helens? No. There is I think you're probably familiar, there's talk of reintroducing them to the North Cascades, perhaps, but not at Mount St. Helens. Somebody asks, why haven't the bears returned? Well, the grizzlies haven't, but the black bears have. So the black bears are there, and I've actually seen them. And then somebody mentioned up earlier that they saw black bears scat. And yes, you can see, especially, oh my goodness. So in the fall, when the huckleberries grow, and Mount St. Helens is just, it's an embarrassment of huckleberries. You'll see, I've run into black bears munching happily on huckleberries, and they're big and fat and happy. And then you see their huckleberry scat all over the place, which keeps you on your toes when you're hiking by yourself. So let's see. So there's a question. I'm thinking ecological succession may never go back to its previous ecosystem. However, the new normal will likely be represented by new homeostasis. How do you think that will look? I don't know. I would think that it will look probably a bit like it did before. So Mount St. Helens, so one of the things that actually, yeah, this is kind of interesting. One of the things about Mount St. Helens that is how it took the eruption to make Mount St. Helens ecologically interesting. So before the eruption, nobody was really paying attention to Mount St. Helens from an ecological perspective. Most of the work, I think, was done at Mount Rainier. There were a few surveys that had been done at Mount St. Helens, but nothing on the order of the sort of rigorous study that's been done there since the eruption. And so once after the eruption, people wanted to be like, well, how does the post-eruption community compare to the pre-eruption community? And in a lot of places, they didn't really have a great, or in a lot of, for a lot of species, they didn't have a great idea, because nobody really knew, because nobody had looked that closely. They just assumed that it was a lot like Mount Rainier. And so in all likelihood, it probably was a lot like Mount Rainier. And so I would imagine that it will go back to looking like Mount Rainier, or like the Mount St. Helens before, in part because because there are eruptions fairly frequently. And so I think I mentioned in the talk that it erupts on average every 140 years. So obviously that's an average. So there's, a lot of wiggle around that. But one of the biologists who worked there, who was one of the first ones, points out that 140 years is well within the lifespan of a Douglas fir, which can live for hundreds of years. And so, and this was one of the things to sort of loop back to the collaborative question about working in Chile, is so when the biologists were down in Chile, they were talking to the Chilean biologists who were looking at trees that had been just pummeled by rocks from Volcan Calbuco, and the trees just looked so awful. They're bark was scarred and their foliage had been torn off. And they just looked for all the world like they were going to die. But the Chilean biologists were like, these trees have lived through several eruptions. You know, there was a huge eruption in 1872 and things like that. And so these trees live through that. They can live through this. And there was some debate amongst the crew there. They're like, oh, I think the trees are going to die. No, they're going to live. And they turned out to live. So likewise with, I mean, as long as, you know, you're a Douglas fir that's not getting mowed down by the debris avalanche or knocked over by the lateral blast clouds, if you're just covered with tephra and you survive that, then that's, you know, part of your natural history. And so I think that one of the things people want to look at, or if they haven't looked at it already, is how, you know, if you can find sort of a volcanic signal kind of in the plants there. So the new homeostasis, you know, brought to you by the old homeostasis. So it'll probably end up, yeah, looking a lot like that. Let's see. I think that's, so there are a couple of questions here. The last two, I think, that I haven't answered. Can anything be learned about recovery of Mount St. Helens from the recovery of Mount Lawson? I will say I don't know the answer to that. Yeah, I think they treated the ecologists treated Mount St. Helens as pretty much a one-off, and so, or, you know, focused on that. Oh, actually, yes. So one of the neat things about Mount St. Helens was that it was one of the first sort of real opportunities to study the recovery of a community to a volcano in real time. And so there was a little bit of, I think, reconstructing at Krakatoa, but other than that, like, Mount St. Helens has done a ton for the field of volcano ecology. So that's, yeah, I think, so I'm going to go out and say I don't think that the Mount Lawson recovery really figured in a lot to the sort of study of Mount St. Helens recovery, but if somebody knows different, they can tell me. I think that is all of them. There's a question of what impact did the down lumber harvesting have on your research, and I am not familiar with the down lumber. If by down lumber harvesting you mean salvage logging, there was a fair amount of salvage logging immediately after the eruption on both public and private forest land, where people went, or loggers went, and were removing down trees to try to salvage the timber. And at one point, I think within the first couple of years, there were something, you know, several hundred log trucks a day leaving the blast area, removing fallen timber before the monument was established. And then they left all of it in place. And so that was something that people looked at. They looked at the effects of forest management practices, pre-eruption forest management practices on the post-eruption recovery. And they found, you know, there were differences between areas that had been clear cut and places that hadn't, and things like that. So yes, the down lumber, you know, salvage logging and forest management did have an effect on the research. And I think that's it. Yeah.
Great. Well, I'm assuming, because there's still so many of you in this room, that if we were in a live auditorium at this point, that there would be a lot of applause. Thank you, Eric, for such a wonderful presentation and your thoughtful answers to all of our questions. For anyone who has any follow-up, obviously Eric's book is available. You can check it out on the UW Press website. Right now they have a 40% off promotion going on. We have really appreciated having you as audience members. If you enjoyed this talk, we hope to put on future talks with coordination with the UW Press and also UW Libraries. And again, thank you, Eric, for your wonderful presentation.
Yeah, thank you very much for having me, and thanks everybody for coming and listening. It was a real pleasure to talk and hear well, read all your questions and see how engaged everybody is with Mount St. Helens. It's really cool, and I hope we all get to go there soon.
Great job, everyone.